And we do know the force function. So the force function was given to us as F max times sine of AT. And the blocks are in contact from 0 to this contact time TC. So now we'll just integrate that. So we'd get F max divided by A, and we get a negative from the chain rule because we get cosine of AT, and we just plug in from 0 to TC. And that's going to give us negative F max over A times the quantity cosine of ATC minus cosine of 0, which is 1. Not 0, 1. So now we're just going to set those two impulses equal because we know if both are impulse and they're the same thing, well, they got to be equal. So we just found impulse acting on the block two ways, and now we just set them equal. So now I would just set my negative F max over A times the quantity cosine AT minus 1 equal to negative 18/7 mv0. And now I just divide by everything on the left side, and I'd get F max in terms of magnitude is going to be 18 mv0a divided by 7 times the quantity. Just to make this positive, I'm going to flip the order around, although you wouldn't be graded for this magnitude. 1 minus cosine of 8 TC. So there's our answer there. Again, we just set two impulse approaches equal. And I just made sure my final answer was positive. That's why I switched the subtraction order. Then for some reason, we're just given another collision that's very similar. New scenario where block 1 is in the x direction with the speed v1 that we don't know. And the 6m block is still moving at v0 to the left. But we are given that after the collision, the two blocks stick together and have constant speed VO. So, actually, what we know about this collision is that it just says constant speed VO, not constant velocity. So it could be going to the left or to the right, but I actually know that since I'm going to be gaining rightward momentum, it's actually impossible for the whole system to be moving to the left after the collision in this setup, assuming V1 is actually to the right. So what we know is that when they stick together, what's actually happening, if we get a V0 as a speed, is the MV1 had to have so much momentum that it actually flips the system around. And we get a direction flip. So now it's just conservation of momentum, just straight up. The sum of the momentum is a constant. So we have an m moving at v1 to the right. We have a 6m moving at v0 to the left. And then we have a combined mass of 7m moving at v0 to the right. So now we'd get mv1 minus 6mvo equals 7mvo. So that means that mv1 would be equal to 13 mvo, or v1 is simply 13 times vo. Which makes sense, because if you had to cancel out the 6m's momentum and then add back to that to get back to its original speed, it makes sense that it's going to be a much larger value. Because the second block was so much more massive, so you need a lot more speed to be able to actually flip the momentum like that. All right, now for points. So this is the MR question, so it's out of 10. Diagrams are 2. So block 2's momentum is 1 point, probably, and both of the two-block system values are 1 point. I would guess the 2-block system points have to be conserved and consistent with block 1 and block 2. So I imagine they do actually have to add together to get this. That's 2. Let's actually write it like this. Add a 2, so you got to get each row correct. All right, now for the derivation, it's out of 5. So you get 1 point for starting from conservation of momentum / impulse momentum theorem. So let's put that maybe right here. You would definitely get a point for finding the final velocity of the block. You would get a point for finding the impulse acting on the block in terms of its final velocity. You would get a point for finding the impulse acting on a block using the force definition with the integral, and then you get a point for a correct / consistent final answer depending on how we grade it. So again, conservation law, final speed, impulse one way, impulse another way, answer. All right, now we have a conservation of energy / oscillator. This question looks weird on first glance, but it's actually not bad at all. So we have 2 springs. One of them has double the spring constant, which is definitely important. And we displace both springs by the same amount. So first question says, if we take this sort of combined spring system, what does the energy profile look like at this time? So we have to use the fact that the potential energy stored in a spring is going to be given by 1/2 kx squared. So we're just going to use the fact that if the extension is the same, but one of the springs has twice the spring constant, then of course the spring with the larger spring constant will store twice the potential energy for the same extension. And then for a free point, it says the block is at rest, so you better not give it kinetic energy. All right, now we're given the block is released from rest at x1, and you begin to oscillate. Derive an expression for the speed v of the block as it passes through the half extension mark. Well, we got springs, and based on the energy bar chart, yeah, we're definitely just doing energy conservation here. So we're going to use the fact that the energy at the start is equal to the energy at the end. So now we're just going to write our energy expression, where at the start it is all potential. Just using the fact that the second spring has twice the spring constant. And then at the end, we still have potential in both springs, we just have the extension. So I'll start by copying the same thing down, just with halving the extension. But now we, of course, are moving, so we also add a kinetic term. So that's a big chunk of things that are kx1 squared in them, so we can get a big like terms combining in these next steps here. So everybody brought a 1/2, so I can make my next simplification as just kx1 squared plus 2kx1 squared equals 1/4 kx1 squared plus 1/2 kx1 squared plus mv squared. Now simplifying again, we got 1 and 2, which makes 3 kx1 squared. And then 1/4 and 2/4 makes 3/4 kx1 squared plus mv0, or I'm sorry, mv squared. So this is 12/4 on the left, so if I subtract 3/4 from 12/4, I get 9/4. Divide by m, and I get v squared equals 9/4 kx1 squared over m. So then I just take a square root, and I get v is the square root of 9/4 kx1 squared over m. But of course, not that we should simplify, but if we did, we'd get 3/2 times x1 times square root k over m. And that's our answer. So I definitely left it as the top form. All right, now we're given the graphing part of the TBR. So in scenario 1, the block oscillates with period t. We're given its position versus time, which makes sense that we release it from rest, so it makes a cosine curve. But in scenario 2, we're putting this block on a surface with friction, and we want to graph the kinetic energy versus time. So again, with anything in terms of kinetic energy, we know that we're really graphing not something k, but we're graphing 1/2 mv squared with respect to time. So we're really graphing the velocity squared. So looking at the fact that velocity is slope, we can instantly find the points where the velocity is 0. So the kinetic energy is 0 every time the spring is at max displacement, which we can tell by these horizontal tangent lines. And you can see that these occur every half cycle. So the kinetic energy is actually going to be cycling at twice the rate. So I know that the kinetic energy has zeros every half period. And additionally, we're given the fact that there is a friction coefficient. So if this block keeps oscillating back and forth and there's friction, energy will keep getting stolen by friction every cycle. So we definitely don't talk about damped oscillations much in AP Physics C, but if you go into a differential equations course, you'll see there's this sort of bounding curve for the oscillation. I should actually do that properly. You'll get some sort of bounding curve that decays. So maybe my kinetic energy starts here, then it decays. So maybe it's something like this. So it's going to be a sine whose amplitude continues to decrease over time. Something like that. Okay, that's not too bad. I'm actually happy with that sketch. Now, in scenario 3, the block is replaced with one of larger mass. The friction coefficient is the same, though, and we want to find how the graph will change. So I spent a while thinking about how the graph would change in terms of the actual rate at which the height decreases, but there's actually a much better relationship, I think, to look at. There are totally valid other ones than the one I'm going to say here. But let's think about the period itself. So we know that for a spring, the period is equal to 2 pi times the square root of m over k. That's just a formula sheet expression. We can derive it from the SHM equation. So if we are increasing the mass, we'll increase the period. So I will say that the graph will increase in period, which is a horizontal stretch. So maybe I'll say that this is a horizontal stretch. And my justification is just the fact that t is proportional to square root of m, which means that as m increases, t increases. So it would definitely get spread out with the larger mass. I thought this was also a very fair question. So let's find our grading scheme. TBR for the diagram. Pretty easy. The diagram's always out of 3. 1, 2, 3. So you have to have a non-zero positive energy for A, double that energy for B, and no kinetic energy. So you didn't have to do 1 bar. You could have done 2 and 4 instead of 1 and 2. You just had to make sure that it was exactly double. They gave you a grid line, so it has to match. Derivation, it's worth 4. 1 point for a conservation of energy equation. Probably 1 point for correct formulas for potential and kinetic energy. 1 point for correct substitution. And 1 point for an answer. So I actually probably earned 2 of the 3 points in this line up here. So I don't think I would have had to write another line explicitly writing out like US1 plus US2. I believe the 2 points are going to be wrapped in probably a correct formula for kinetic energy and spring potential, and then actually plugging in properly. And then, of course, the answer is the last point. The graph. This is interesting. So for the graph, it's going to be out of 3 for the TBR question. So first, it's got a decay. I definitely would imagine one of the 3 points is for decaying. You probably get 1 point for drawing a sine curve of some sort. And then you get 1 point probably for the period being 1/2 of the original, starting at 0. So I'd probably say sine curve with 0, 0 on the graph. So this appears to be what I think the 3 points would be. We'll see how close I am when the guidelines come out in June. And then the translation is just 2 points. One for an indication, and one for a justification. So there, you could do other features. Feel free to ask about what features you commented on in the below, and I'll evaluate, or others will evaluate them for you. Again, the one that I think is the easiest to get is the fact that since the period is proportional to the root of the mass, if you're increasing mass, your period increases, so it stretches out. I don't know if you explicitly had to say if it stretches out, or if you could say period increases. I feel like anyone knows the word period is referring to the horizontal distance, but just to be safe, I wrote it was a stretch. All right, now for the lab question. This is the easiest lab question I've ever seen. So I hope a lot of us had success on this. I think this could arguably be one of the easiest mechanics FRQs I've seen in my life. A box is connected to one end of a rigid rod. Both the box and the rod have negligible mass. If it didn't, this would be a much more difficult problem, but still doable. The center of mass of the block is displaced some distance and it swings to the bottom. We want to find G using this with a motion sensor. So we're given access to a motion sensor as well as a meter stick. And it's prompting us here to use the meter stick to measure different heights, and we have a motion sensor, so we want to measure something. So, oh, and it explicitly says the motion sensor measures speed. So I'm not sure what other things we could really think of other than measure the change in height of the system center of mass, h, measure the speed v when the system collides with the stopper, meaning at the bottom, and to reduce uncertainty, repeat for multiple values of h. I mean, yeah, there's not too much to it, right? This follows the exact format I said we'd see on the lab question, right? An extremely obvious set of things to do, right? Measure blank using blank, measure blank using blank to reduce uncertainty, repeat for multiple values of blank. Now we're gonna describe how we analyze this with a linear graph to find G. So this is once again just energy conservation. So we use the fact that 1/2 mv squared at the bottom is equal to mgh at the top. So we'd get v squared is equal to 2gh. And now we just got to graph that because I have data of v and h. So I would actually say graph v squared versus not h, but 2h. I know some of you aren't going to like that. Some of you don't like doing the slope is your answer way. So mine actually guarantees your slope is just g. But I imagine the more common answer is graph v squared versus h. The slope is equal to 2g. Use that to solve for g. So again, I wrote this way so I could do v squared is equal to 2h. Sorry, g times 2h. As I said, that this now follows y equals mx plus b format. Pretty straightforward again. This is like the energy conservation equation that's the most common. Obviously, there's so many other things you could have graphed for this. If you square rooted it, you could have done that. V versus square root h. All that stuff. All right, now the block is launched at a speed, or sorry, now it's launched upon reaching the floor, and it's going to go some distance before friction stops it. So all we're given is the height that it swings from, and then we're given the distance it travels. So yes, there is kinetic energy here, but we can once again bypass it, just due to the fact that we're given the initial energy, mgh. So what's happening is the potential energy is getting stolen by friction. So our gravitational potential, mgh, is getting stolen by friction, and friction is just going to be the frictional force times the displacement, which is x max. And then since we're on a flat horizontal surface with nothing strange, our friction, which is mu times the normal force, is just mu times mg times x max. And basically everything cancels. So we're just given h is equal to, well, the mg's both cancel, so this is just mu times x max. So that means that what I want to graph is h versus x max, and my slope is just mu. You could graph, of course, x max versus h, and the slope would be 1 over mu. All right. Now, of course, we don't need to see me sit here and plot points. So we will take a quick production break for me to do that and scale my graph. This is not something I need to transform. So I'm just going to literally plot this data and be right back. All right, we're back. This was definitely the hardest part of the whole exam, graphing these points. I personally hate plotting points, and I probably didn't even do it the best, but of the entire exam, I literally found this to be the hardest, is plotting the points. But regardless, here we are. So now we just got to draw a best fit line. And the best fit line, it's going to be pretty good in this case. So I'm just going to try to get about half above, half below, maybe something like that. That looks pretty decent to me. So there's my best fit line. So again, notice I graphed height with meters, so I labeled my variable and my units. And I drew my origin, so a nice linear scale. I plotted my points, and I drew a best fit line. So now using that best fit line, calculate mu. So this is very easy because it's just the slope. So I can just say from Desmos, we should say that regression was used. So I just did y is equal to 0.38x plus 0.03. So that's what Desmos spit out when I put this into the table. Of course, you could do your slope by hand. I know there's a lot of people who like to do that. No problem. But then I just know that mu is actually equal to my slope. And that's 0.38. Nothings. Because mu is just a coefficient, so it's nothing. Because again, the relationship we derived was this fact that h was equal to mu times x max. All right, now for points. 10 points in the experimental design. 2 points for A. Did you measure the height and speed? Did you do multiple trials? Great, there's your 2 points. Did you graph a correct linear relationship and relate that relationship to G? Great, that's another 2 points. Did you figure out this relationship was linear already? That's 1 point. Did you, no matter what you graphed, even if it was wrong, did you scale your axes with labels and units? Did you plot the points accurately? And did you best fit line that makes sense? If so, that's 3 points. And then for your 2 points here, did you relate your slope to mu properly? And then did you get a reasonable correct answer for mu? So there's all your 10 points here. And then lastly, we have question 4. This is the only one on the test that I felt would really give people some trouble. And I know this because I didn't even instantly know the answer to part A. So I did what I told you to do when you don't know, And that's actually solve part B of the QQT first. So I'll say I couldn't really find the insight for part A when I first saw this problem. I only found it after kind of knowing what the answer should be, and I worked backwards. But now we're going to explain it in order. So we have a classic setup. We have a disc and a ring, or deep disc and a hoop, racing up an incline sort of thing. But this time they're given the same speed, and we see that the ring goes higher, and we're sort of interested in that explanation. So let's figure it out. What it wants us to look at is the static friction forces between the disc and the ramp and the ring and the ramp. So, looking at this, energy won't be totally helpful, I don't think. I'm sure there's an energy solution out there. But the frictional force doesn't do... the static friction force is not going to be totally helpful in this case if we're just looking at mgh and 1/2 mv squared contributions. So what we should look at is what static friction is actually doing. So first I'm going to draw free body. So I know that on the ramp, I have some object, and it's in contact at exactly 1 point. So what the only relevant forces when it's going up the ramp is the fact that we have a component of gravity pulling down, mg sine theta. And this isn't a draw free body diagram question, so I'm totally allowed to just put mg sine theta this way. And then a frictional force. So we are given the fact that it's rolling without slipping, which is really important, because if it's rolling without slipping, it means that this point right here, the contact point with the ramp, has 0 speed or velocity. Because the translational velocity and the rotational velocity at both those points, it's sort of a vector sum that cancels. So we're given the fact that this point is stationary. So if this point is stationary, what that means is that the friction force would try to prevent it from slipping. So if it slipped, this point, if it's just like a box on a ramp, is going to slide down. So that means that the frictional force actually acts up the ramp, sort of aiding its motion up. So this is our free body diagram. So the key here is that mg sine theta is what's slowing down the hoop slash disc, but static friction is opposing it slightly. We see that static friction doesn't win, because eventually it will stop on top of the incline. So we know mg sine theta is definitely bigger than static friction, but the extent at which that occurs is what's causing this change between the heights. So really, we see that since the hoop goes higher, the resistive force has to be bigger for the hoop. The thing that's fighting mg sine theta has to be bigger for the hoop. So both objects are experiencing both a gravity pulling down the ramp and static friction pointing up. But what's different is that since the hoop is going higher, it must have a stronger force of friction that's fighting mg sine theta more. So the effective acceleration is less. And all that means is that Fs is going to be greater for the ring. So the ring has to have a bigger friction force because it goes up. Because the friction force is what's opposing mg sine theta. I know we're used to friction being the thing that's opposing motion, like in the translational case, but in this case, the static friction is actually fighting the coming down the ramp force. Because if this was a translating problem, actually static friction would also go down the ramp, and it would be the two forces aiding each other. Now, I actually think it's much easier to do the derivation first for this. So I would definitely have not started with A. Like I said, I didn't know how to do A initially. So I'm going to go on to B. And we're talking about frictional force F exerted on just a arbitrary cylinder of rotational inertia I. So if we want forces, energy is not probably the way to go. we should just set up a system. So I'm going to set up side by side F net equals MA and net torque is I alpha. So I can make myself a linear system because the net force is just going to be the mg sine theta contributing to the acceleration minus the static friction fighting the acceleration. And then I alpha is going to be equal to, well, it's just the frictional torque. And that's just the frictional force times the radius of the cylinder, because the frictional force acts at the radius. And then we can also make this substitution that instead of alpha, we can write A over R, the no slip condition. And that'll allow us to get rid of this A. So summarizing, we have MA is mg sine theta minus friction. And we have IA would be equal to F times R squared if I multiply both sides by this R in the denominator. So what that allows me to do now is in the second equation, I can use this and solve for A because I don't know A or F. So A would be equal to FR squared over I. And then I'll substitute away the A in the force equation for that, and I would get M times FR squared over I is equal to mg sine theta minus F. And then I'll collect all of the F's on one side, and I would get F times the quantity, mr squared over I plus 1 is equal to mg sine theta. And then our frictional force is just going to be mg sine theta divided by all of that stuff on the left. And there's our answer. So they actually didn't ask the consistency question in part C this time, which was kind of interesting. Because I actually thought it would be nice comparing. So I actually did this on my own. And what I saw is that if I plug in a really, really, really big rotational inertia into this, so like infinity, I would get mg sine theta as the frictional force. But if I plugged in a really, really, really small number, like 0 into this, I would get infinity in the denominator, so I'd actually get 0 for the frictional force. So what that tells me is that low I has low friction and high I has high friction. So that's consistent with this explanation above. I'm sure there's way more explanations of this part A than my forces approach. I used the fact that it goes higher, like that is a fact that I started with. If not, you could also use a rotational inertia argument to approach this as well. All right, in a different scenario, the disc and the ring slip. So we're asking what's the force comparison if they slip against the ramp? Well, if they're slipping, it's not static friction, but it's kinetic. So the kinetic friction force is equal to mu k times normal force. And this is a set value, so static friction can be whatever it needs to be to make the system work, up to mu Fn, but kinetic friction is fixed. So mu k, that only depends on the surfaces rubbing against each other, which is the same because the cylinders and ramps are the same. And same thing with the normal force. That's also the same because both ramps are the same and both masses are the same. It's going to work out, mg cos theta in actuality. So that argument, we can just say that since the objects are slipping, they're experiencing a kinetic energy force Unlike static friction, kinetic friction does have a set value, and the things that affect kinetic friction are the same for this. So again, I would say that F of the disk is equal to F of the ring in the slipping case for that reason. All right, now for grading and my final thoughts. So, QQT, 1 point for a correct selection. So A is worth 3. 1 point for a correct selection. Sometimes you aren't totally locked out of justification points if you pick the wrong thing. So, I feel like this is where points will vary, because if you did not use my explanation, you won't get points relating to forces, it seems, if you took a different approach. So I wouldn't be so harsh, like thinking about how you did with this explanation point, because there's such a wide range. So this is why when I read, I really want to be put on these sort of open-ended questions, because I love to hear the out-of-the-box explanations for this that I would never have thought of. I believe my point, I'd get a point here probably for saying that by finding the direction of the forces, and I get a second point for explaining that this thing about friction being the resistive force to the mg sine theta. So the hoop going higher means it has more resistance. So that would be my 2 justification points. So again, you get 2 justify points here. And typically, you can earn those without the correct selection. Now for the derivation. I imagine you get 1 point of the 3 for stating Newton's second law for rotation/translation. You would probably get a point for either correct force and torque equations or a correct application of the no-slip condition alpha is A over R. And then you get a point for a correct answer. And then for your modification, you get a point for saying that the forces are equal, and you get a point for a valid justification to get you to 8. All right, and then just to review the entire exam here. It's out of 40 entirely. So, momentum question 1, I thought that was very standard. Not anything strange there at all. I think we could do pretty well on that. Maybe miss a couple things with the impulse. The spring question, again, I thought that was also pretty straightforward. Nothing strange there. Get your 12 points on the TBR. Although the graph and I think C and D is where things start to get a little bit dicey, perhaps, for the spring question. Lab, I don't really see any issues with that. But then here's where it gets really tricky, I think. Being able to live problem solve, I definitely flipped between disk and ring having more friction before I actually just buckled down and derived it. This is a very difficult qualitative part. I actually really like this question. You might not agree with me. You might think this is an awful question because you got it wrong. But this is a good question. I think this is where a lot of students will mess up. This might be the 4 and 5 differentiator type question, is could you manage to squeak out some points on this question even if you got stuff wrong? So we know nothing about the cut scores, but my guess would be if you got this form, because again, cuts are different by form. If you got this form, you're probably looking at trying to get 70% and above at least. That's kind of my guess with this, because I thought this was a relatively easy set, especially compared to the chaos of some of the AP practice ones we've seen this year. But yeah, hopefully we had some success with this. I thought it was pretty normal. Let me know.